Hello, thank you for joining us for a conversation with two members of the team that have brought us a new image of the distant universe. The Hubble Extreme Deep Field brings into focus galaxies that formed just a few 100 million years after the Big Bang. This new image is going to tell us a lot about the universe at very, very early times, up to 13.2 billion years ago. Today we'll be talking about this new image, how it was created, and what it means. Joining me today is Michele Trenti with the Kavli Institute for Cosmology at Cambridge University in the UK, and Pascal Oesch with the University of California at Santa Cruz. My name is Bruce Lieberman. I'll begin with a few questions, but I'll also be asking questions from the public. So to begin, I'd like to ask both of you, and please jump in as we begin, what does this new image show that Hubble's previous deep field images do not show?
Yeah, so hi Bruce. So essentially this new image that we have created, this XDF image, extends our view of the universe to longer wavelengths than what we have been able before with its predecessor, with the Hubble Ultra Deep Field. And so this is very important if you want to study galaxies at very early times, because these galaxies are completely invisible to our eyes and were invisible in the previous image in the Hubble Ultra Deep Field. And so by extending the wavelength range of this image to the near-infrared, we can now probe to much earlier times, to, as you said, more than 13 billion years into the past. And so we can see how galaxies, how the universe was looking like, how galaxies were looking like at these early times, and how galaxies were building up, and so on. And so, yeah, this is a fantastic new image. Michele.
And yeah, I would like to add that in the past we had released ultra deep field images of this location of the sky, both in the visible light and in the near infrared.
And that was in 2009?
Yeah, and 2009 in the near infrared. This is the first time with the XDF that we combine both the visible light and the infrared into a single image. So we are getting a panchromatic view of how the universe looks like, which is allowing us to study galaxy evolution not only at the very beginning of the universe, but also all across cosmic time.
Now tell me, what have you seen so far in this image that really particularly impresses you? And I'd like to ask both of you that question. Pascal first.
Yeah, so when I first started to work in this field of research, we didn't have the V3, this new camera, yet. So we had its predecessor, which was called the NICMOS camera, and this also had the capability to look into the near-infrared light. But it was 40 times less efficient, essentially, than the new V3 camera. And so we were trying to do the same thing. We were trying to find galaxies about 800 million years away from the Big Bang. And we also found a few of those, and just a handful, over the same part of the sky that we are looking now at with the XDF. The problem was that these sources were just really at the limit of our detection of our previous NICMOS image, and we couldn't really see them very well. They were very faint, and so on. And then as the new data came in, the first data with 3IR, these same sources that we had identified, they were just booming at you, and really that just blew me away. Essentially, the way, the clarity and the contrast with which we could see these galaxies 13 billion years into the past, that was just really impressive to me, and yeah, really amazing. And so now that we combined all this to the XDF image, essentially everybody can go out and look, and look for these sources. They are visible there, and so people can look 13 billion years into the past. Everybody can do it.
And what strikes me about this image is the amazing diversity of galaxies that we can see. We can see thousands of galaxies. And keep in mind that this is only a tiny patch of the sky, much smaller than the full moon size. And yet, so many galaxies, so diverse, this truly shows that our universe is a really big place and a fun place to explore.
Now, this image is showing galaxies that are, what is the range of time that you're looking back? Some galaxies in the image are closer to us and some are farther away. What is that range?
Well, this is a very good question. Most of the galaxies in this image are between 5 and 10 billion light years from us. So they formed from 8 to 4 or 5 billion years after the birth of the universe. There are a few relatively nearby galaxies in this image, and then a handful of galaxies that were formed within the first 600-700 million years after the Big Bang. About 15-16 of those seen in this XDF image.
So I'd like to back up a little bit with a few basics, and then we're going to turn shortly to questions from viewers. But help me understand, and our audience, where in the sky this deep field is, and you said it's an extremely small patch of the sky that you're looking at. So tell me about that, and then also how you created this image. So this is not a new observation from Hubble. It's a processing data that's been collected over a decade. So if you can just go into some of those details.
Yes, so I can start by telling you that this is an image in the southern skies in the Fornax constellation, and its size is about 2 by 2 arc-minute square. To give you an idea, it's about 50 times smaller or so than compared to the full moon size. So tiny bit of the sky.
Mm-hmm.
So to tell a little bit how the image is constructed.
Yes, please.
From all the information available in the Hubble archive.
Exactly. So the main point here is the Hubble archive. So whenever Hubble takes an image, essentially the data is sent to the ground to the Space Telescope Science Institute that runs Hubble. And it's calibrated. They do a first calibration there, and then it's put into the archive. And essentially everybody that wants, it's freely available to everybody, can download images from Hubble and can look at these images. But what we did now is we essentially combined all the images. There are more than 2,000 images that went over this one place in the sky. And so we downloaded all these. We looked essentially at all of them. We have to make sure that there's no artifacts, that everything looks okay. Then the next step is we essentially have to align those images. We have to make sure that a given pixel essentially always looks at the same part of the sky. And so you have to do this with some computer programs. And then essentially we can sum up the images. And adding frame after frame, you look deeper and deeper into the universe. And you see more and more clearly what is going on in the universe, essentially. And so, yeah, it's essentially a 2 million second exposure in the end that we combine with all these images. And so the last step essentially is to create a color image, because what I guess people don't really appreciate is that astronomers, they don't see, we're not working with these nice colorful images all the time. When Hubble takes an image, it's black and white. So we have a black and white image, and the way we create a color image is by essentially we select a different part of the wavelength range. Sort of, we put a filter in front of the camera and select only blue light, only red light, only green light, and so on. And so we have a set of different images, essentially 7 different images that probe different wavelength ranges, so different parts sort of the rainbow. And then we combine those to create this colorful image here. And it's essentially a false color image, because what you see in this image as red light, galaxies that appear to be red in this image, we would not be seeing them with our eyes. They are invisible to our eyes. So essentially that's how we created this panchromatic, this long wavelength range view that Michele was saying.
Yeah.
So it combines both optical and infrared?
Exactly.
It combines both optical and infrared. So if people compare with the previous Hubble Ultra Deep Field images, this image looks more colorful because we use a wider baseline of wavelengths. So we are able to see more clearly the color differences between different galaxies.
So the latest Hubble Deep Field, Ultra Deep Field, was released in about 2009. Give me a comparison for how far back that took us to how far back this current image takes us.
Yeah, so
about the same.
they are the same, exactly. So the image that we released, that our team released in 2009, that was only the near-infrared part. So that is, as Michele says, took us back to the same time. What the new image that we have released now combines both optical and near-infrared. And optical, essentially, there was already a previous release, of course, in 2003. That's the Hubble Ultra Deep Field that everybody knows about. But now, essentially, we combined all the data that was taken between 2003 with the ACS camera. There was more optical data as well that was taken. And so the previous Ultra Deep Field was, I think, a 1 million-second exposure, and now we have a 2 million-second exposure. So we combine everything. But compared to the 2009 image, it takes us to the same distance. It's just we cover a much larger wavelength range now.
And I think it's important to add, though, that despite the fact that this XDF image only takes as far back as the previous one, the one that we released in 2009, because we have this deeper data in the visible, we are able to identify the most distant galaxies with a greater confidence. And this is because if we have a very distant galaxy in this XDF image, we see it only in the infrared filters. The light has traveled so much to reach us that it has been stretched into the infrared. There is no visible light coming from galaxies that are only 700 million years after the Big Bang. So by going deeper in the visible, we are able to discriminate better which are the galaxies that are truly very, very far away from us.
Okay, I'm going to move to viewer questions right after this next question, but I wanted to ask you something fundamental and why you know it's amazing that obviously that we can see this far back, almost approaching very, very early times. But why is it important for researchers like yourself to examine this period of time?
And you know, the properties of today's stars, galaxies, and black holes all depend on their formation history. And the first stages in particular of the formation of galaxies early in the life of the universe are so important to determine the transition from a very homogeneous, boring place with all dark, no light, and the appearance of the first stars and galaxies. The properties of those early generation of stars are what then are setting the universe as we live it in today.
Yeah, essentially we can probe really the origins of the universe we see today, and we see those little blobs, which are the seeds of the big galaxies that we see today, and of course are the sites where all the stars that we see are formed around us. And so yeah, so that's we just see back to the origins essentially.
And maybe another important aspect of our search for the most distant galaxies is that theoretical modeling and computer simulations are very easy to do starting from the initial conditions immediately after the Big Bang. And then the simulations and the models become more and more complicated as the time passes. So by having observations at the earliest time, we have unique possibility to compare the modeling with what the universe is really about, and this way refining our understanding of how the universe was formed and evolved.
Terrific, terrific. Well, I have a question from a viewer, and it's I think it will take some explaining, maybe to explain why we can see some things in the distant universe and not others. And this question is that if everything is expanding in the universe and everything is getting farther away, and we look farther back in time to when the universe was smaller, why can't we see, say, our own Milky Way galaxy at an earlier time? And Michele, if you can talk about that.
Well, we can see these distant galaxies when they were young, when the universe was young, because light only travels at a finite speed. So the more distant an object, the longer the time that the light from that object needs to reach us. To give an example, if the object is nearby, like our own moon or the sun, it's a short time, about 1 second in the past for the moon, or about 8 minutes for the sun. For these very distant galaxies in the Hubble Ultra Deep Field, it can be 13 billion years. So our own Milky Way, we see it with some as it was in the sort of relatively recent past for astronomical timescales, just 100,000 years ago. Of course, we can see distant galaxies that are, or that we think are similar to how the Milky Way was in the past. And there are some here in this beautiful XDF image, such as a magnificent spiral about halfway high in the image on the left side.
So these objects that we're seeing at very early times, all of these objects are moving away from us, ultimately. So we cannot see the galaxy that we're in at an earlier time because that galaxy has been traveling with us.
Yeah, that is traveling with us. The light from our galaxy in the past is moving away from us. It's reaching other galaxies. So maybe there are other observers looking at how was the Milky Way 10 billion years ago.
Okay, very good. Now, another question that came in from a viewer asks about the shapes of these early formed galaxies. Now, if you look at some of the oldest objects in the image, they just kind of look like blobs. Now, does that mean because they are so distant and faint, or because they're actually shaped that way? They're kind of undefined early galaxies. Pascal, if you can talk about
that. So there are different things here. As we look back for these blobs that people are seeing, these bright blobs, these are really elliptic. We call them elliptical galaxies because they're essentially two distinct shapes in galaxies. Ones are spiral galaxies like our own Milky Way, and the others are elliptical galaxies. And typically, elliptical galaxies are not forming stars anymore, and spiral galaxies are still forming stars. And so one of the big open questions, or one of the big questions of astronomy, of galaxy evolution, is how do you transform these spirals into these big fuzzy elliptical galaxies? And so that's a question that astronomers all around the world are still working on and trying to understand. And the way we're trying to understand is exactly, we look back in time. And so you see how many of those spiral galaxies existed, how did they look like, how many of those elliptical galaxies existed, how did they look like, what kind of stars would they host, and so on. Okay, Michele?
No, but I just wanted to add, though, that as we look back into the past, of course, galaxies were smaller because they didn't have sufficient time to assemble and reach the size of the Milky Way. So, for example, the typical galaxies that are 600-700 million years after the Big Bang that we see in the XDF image are probably around a 10th, a 30th of the size of the Milky Way.
Exactly.
And of course, because they are so distant, they also look fuzzier. But they have intrinsically less structure. They are less developed than our own galaxy.
Yeah, but it's amazing that, in particular, there's one galaxy in this image that we see. It looks like a little disk galaxy as we see it from the side. And so definitely, even at these early times, there were already some interesting structures developing in these galaxies. It's just that we cannot resolve them very well yet, also because they are so far away. Yeah.
Yeah, we will need the next generation of telescopes, such as the James Webb Space Telescope for this.
The James Webb Space Telescope, which is scheduled to be in orbit probably early next decade.
6 years or so, 2018.
6 years, maybe late this decade, if we're lucky.
Exactly.
Okay. So here's another question. What do you imagine to be the limit that we can look back in time? And what do you think we would see at that limit? Now, my understanding is that the farthest that we can actually look back is the cosmic microwave background. So if you can talk about that, Pascal.
Yeah. So the cosmic microwave background is really the limit. All light essentially was that we can see last sort of originated from that sphere, from the cosmic microwave background, and so that's 400,000 years, sorry, after the Big Bang. And now with Hubble, of course, it's not a microwave telescope. Hubble is a telescope in optical and near-infrared wavelengths, and so we can see galaxies. With Hubble, essentially, we are with this image, with the XTF image, we are at the limit essentially of what we can see. It's 400 million years or so after the Big Bang. Just because, as Michele was explaining before, the universe is expanding, and as the universe is expanding, the light is shifting to longer and longer wavelengths, to redder and redder light, and it's just, as you go further back in time, it just escapes the view of Hubble, and that's really where we need James Webb, and that will be a really big milestone again for extragalactic astronomy and for pushing further back in time.
Michele, if you can just essentially describe what the CMB is and why it's this curtain beyond which we cannot see with available technology observational technology.
Okay, so I can start first by describing the CMB and then just hinting that maybe later this century we can indeed go beyond the CMB. But first, what is this cosmic microwave background? So the universe at the beginning was a really hot, compact collection of plasma. So the nuclei of the atoms were separated from their electrons. Everything was in a very high temperature state. So the photons that were produced, because this was a hot gas, were interacting with electrons, other particles, were not escaping. As the universe expands and it cools down, we reach a point at around redshift of 1100, or about 500,000 years after the Big Bang, when there is this decoupling between radiation and matter. At that point, the photons can escape freely from the plasma, and then they can travel and lose energy and move toward the redder and redder wavelengths. And so by the time they reach Earth today, after 13.7 or so billion years, they are in the microwave range of wavelengths, and they can be picked up with detectors today. And so we can learn how the universe was just 500,000 years after the Big Bang. So to go back to what is the farthest that we can see, maybe later this century, when we will have detection capabilities for gravitational waves, we will be able to see the equivalent of the cosmic microwave background, but in gravitational waves. And this will probe the epoch of inflation, so really the very, very beginning of the history of the universe, within the first 10 to the minus 40 seconds or so after the Big Bang. So that is a zero followed by 40 zeros, 1 seconds.
Fraction of a fraction of a fraction of a second. Yeah.
It's really so hard to communicate how tiny this fraction of time is.
Mm-hmm. Okay. All right. So let's see here. Let me look at a couple more questions. Is there anything Hubble can see that might prove or disprove some of the theories of existence? So, for example, string theory or multiple universes. That's really a different part of cosmology, isn't it? The Hubble Extreme Deep Field is looking back in time at some of the first objects that formed, but it's not really going to address some of these more fundamental questions. Is that right?
Yeah, that is perfectly right. There are other astronomical probes that can try to understand fundamental physics. We can see the distribution of galaxies on the largest scales, but those require typically to image much larger areas of the sky compared to the tiny Hubble field of view. So we really have with Hubble a very, very deep view of the distant universe, but it's limited to only a tiny fraction of the universe.
So for example, a new project, the Dark Energy Survey, is going to be looking at the expansion of the universe and taking a survey of galaxies over a much bigger patch of the sky. And
Yes.
that will help us address that fundamental question, what's driving the universe apart. But the Hubble Extreme Deep Field, it's really well, I think I read that it's like looking through an 8-foot straw at a little patch of the sky. I mean, it's very, very small part of the sky, which makes it even more amazing because it opens up into this huge vista of early objects, even in that tiny spot. It's really hard to, I think, grasp, to imagine that. But okay, well, let me turn to a couple of other questions that have come in while we've been talking, and that is. Okay, it's kind of a fundamental question, but how do we actually know how far away these images are, or the objects in these images are? So if you can return a little bit to, I think, Michele, you had talked about light traveling at a finite speed, and we're able to measure distances that way.
Yeah.
You can just briefly state that again.
Yeah, so light travels at a finite speed, so the more distant the object, the further back in time we look at. And in addition, as light travels through these immense distances, the photons lose energy. So what is emitted as pretty energetic photons in the ultraviolet, so higher energy, bluer color than human eye can see, by distant galaxies 13 billion light years or so from us. By the time those photons reach us, they have moved across the whole range of the human eye perceptions, and they have arrived in the near infrared, so redder than we can see. By looking at the colors of the galaxies, we can get an approximate idea of what the distances of those objects are. And then, of course, we can go back and stare at this field with our most powerful telescopes on Earth, in Hawaii, on Mauna Kea, or in Chile, and we can try to take a spectrum of the galaxies and measure the exact frequency of the light that reaches us, and from that we can infer the precise distance.
Yeah, and so the amazing thing of for instance, JWST will also be that for these very, very distant galaxies that we just see now with the XDF, we can exactly take spectra, as Michele was saying, and we can determine exactly the distance. Now that we have some uncertainty on that, but yeah.
If I take the next generation of telescopes, so you're talking about the James Webb Space Telescope,
That's right.
looking at the same ultra deep field, for example, we'll be able, through spectroscopy, we'll be able to more accurately, more precisely pin down the distance. Will it also be able to say anything about the composition, the chemical composition of these distant objects?
Absolutely, yes.
So what right now appears like fuzzy blob in the Hubble image will be resolved in greater detail by the James Webb Space Telescope. So we will learn more also about the internal structure. We will be able to establish to greater confidence that there were disk galaxies like our own Milky Way back 13 billion light years ago.
Yeah, and you were asking about the chemical composition. Exactly, the spectra will tell us about this, and so it will tell us when did all the metals and all the heavy elements that essentially Earth and we are all built up from, when did they form? And so we can do that going back to these very, very early times.
Well, we will end there on that note, because there's some very exciting research coming in the future. A lot of it hinged on the upcoming James Webb Space Telescope. Thank you for joining us today. We really appreciate you discussing this exciting new image, and we're looking forward to more. Thank you.
Thanks a lot. Bye.
Bye.